This is a quick wrap-up recording of all the programs that you would have covered in week 1. So I'm just going to open them up here, and we can see here the different programs that we've done. Now I'm not going to go through the Hello World program or the name and address program. They're so simplistic that there's really no point in going through them. I am going to take a look at this simple integer operations one though, and just looking through some of the other ones. The printing your name using single characters, that caused a bit of confusion for people in the way that they went about it, so I'm just going to take a quick look at that as well. Special character constants, I'll just mention something on it. Viewing numbers as hex, minimum field width, maximum size number, these unsigned, and a few things. I'll be making a few comments about those as I go as well. So for any of the programs here in week 1 that you're not sure of, or that perhaps you thought you knew, and I may be pointing out something that may not have been obvious at the time. So that's what the point of this recording is. It'll probably take a little bit of time because I'll have to go through all the programs, but I'll pause as often as I can to write sections of program where you don't need to be watching it. So starting with the simple integer operations one, you were asked to declare 3 integer variables x, y, and z. Assign a value of 7 to x and a value of 2 to y, and then z assigns the value of the addition of the two numbers, and we can see that there. So the output, the printf, the output should look like 7 plus 2 equals 9. Now we need to add to the program. This is important, not write a new section of a program. Add to the program above with a subtraction, a multiplication, and a division. So that's what we're going to do there, and then we're going to figure out this one, the percent operator. It's the modulus operator is what it's called, and we'll take a look at that as well. So I'm just going to pause for a moment while I write the basic body of the program. Now, so what I've written here is the basic body of the program. We have our int main void, and we have our system pause, return 0, and so on, or stdio.h. We've made 3 variables, 3 integer variables called x, y, and z, and then we've set x to the value of 7, or assigned the value 7 to x, assigned the value 2 to y, and then we've said z is assigned the value of x plus y. Okay, so z will now hold the value of these two added together, which will be 7 plus 2, which will be 9. Okay. Now in our printf, we want to include 3 variables. So we want to say, in effect, what we want to see happening on the screen is going to be 7 plus 2 equals 9. So we need %d here for the first variable, which is x, which is going to be the 7. Then we need to put our plus sign so that our plus sign gets printed out. Then we need another %d to deal with the second variable, which is y, which is going to be a 2. Then we need our equal sign, and then we need another %d, a final %d for the z, which is going to be the addition of the two together. So that's our printf statement there, and we'll just give that a run. Okay, and we see that 7 plus 2 equals 9, and that's exactly what we wanted to see. Now, what you're asked then to do is to add to this program the above subtraction, multiplication, and division, as we see them there. Now, in this case, what we need to do, we're adding to the program, so we're going to start doing more down here. Now, all we really need to do, remember that these things are variables, and therefore they can vary in value. Now we don't need, as it happens, to vary the value of x and y, so there's no need to redo those. I'm just looking at my notes here as I was going through some of the ones. Paul Culleton, I think in your program, what you had done in each case, nothing massively wrong with it, but you had continued to write this in each case down the way. So on. Okay, there's no need to redo those. If you're not changing the value of them, there's no need to rewrite them. Okay, the only one that's going to change in value here is the z, so that's going to say z is assigned x minus y this time. And again, no need to come up with new variable names or anything like that, or no need to write a new program. And so all we do then is we can literally copy our printf here, paste it down here, and change our plus to a minus. And we'll run that, and we now see that 7 minus 2 equals 5. Now remember that minus or plus that I put in there, that's just text. It's not an actual mathematical operation in that particular case because it's inside these quotes. So I could write the plus in there, but it's still the minus operation that it's going to do. So do be wary of that, that your printfs, there's no real checking of mathematical operations within them, they're just text. So that's all you really have to do in that case, and then we can just do a copy of that. And our next one is a multiply, and so we change this to a multiply, and we run that, and we can see 7 multiplied by 2 is 14, that's fine. Our next one is a divide. Important to note the answer of this one. 7 divided by 2, it says 14, and the reason for that is because I've changed the divide here, but I never actually changed the operator here. So change that to a divide. Now we'll run it properly. And it says 7 divided by 2 is 3. Now most of you would expect that that would be 3.5, but this is a very, very important operation. When you're doing a divide, if it's an integer on the top and an integer on the bottom, okay, or an integer on each side, the result will be an integer, and so 3.5 is not an integer, and therefore it literally just cuts it off. So it doesn't matter if it's 3.99, that will be turned into just 3 on its own. The 0.99 would get cut off. It's not that it rounds up or rounds down to the nearest one, it literally just chops off that section. And that actually brings us on to the next one, which is the modulus operator and exactly what it does. Now, I'm going to worry about what goes in here in a minute. I'm just going to leave it blank for the moment, and we'll just look at the answer that we get. So, using the modulus operator, we get an answer of 1. Now, what has happened there is that we've divided 7 by 2. It's gone in 3 times evenly, and then there is 1 left over, and that's what the modulus operator gives us. So the modulus operator is only works with integers. It doesn't work with floating point numbers. So for that reason, you may think that it's not particularly useful, but actually there's a number of the programs that you're going to come to in the next while. You'll probably have forgotten that you use this operator, and it'll be vitally important to solving some of the problems that you have. So do take note of it. One of the things we have a bit of an issue with, though, is actually writing the percent sign to actually come out as text. The problem is that when we write a percent sign, C program normally expects that the letter following it, such as in the case of the D here, is an important thing that we're going to actually interpret some variable later on or whatever. What happens in the case when we actually want to put a percent sign out on the screen? Well, what you do is you put a percent sign and then you put another one straight after it, so that it says, okay, sees the percent and says, okay, the next thing is important. Oh, the next one is a percent as well. That means they obviously want me to print the percent out on the screen. And then finally we go back to our percent D here and our percent D here. So if you actually pack these tied up against each other, you'll see that there's 3 percent signs in a row. The first one is to warn us that the second one is to be printed as text, and then the third one here is to warn us that the next letter is a D, which tells us to interpret one of these variables as an integer. Okay, so do be aware, or do be wary of those that they can catch you out. So 7 modulus 2 equals 1. Very important. That may seem a little trivial right now, but I assure you that there's an awful lot of questions in the next few weeks where that modulus operator is the appropriate thing to use, and you may not be aware that you should be using it. Okay. Now I'm just going to open one problem there. I'm going to open Patrick Brennan's problem because it's something I've noted down here. So I'm just going to pause for a minute. Now what I've done here is I've opened Patrick Brennan's program, which does actually work. If we run it here, we can see that they all come out. He hasn't managed to get the percent sign in there, but apart from that, all the other parts work. The only issue is with the way that he's gone about it here, and in fairness, because I actually mentioned functions quite early on, what Patrick has tried to do here is to use a lot of functions, somewhat unnecessarily as it happens. So he's made the 3 integer variables, and he's gone and done the plus thing, and he's printed that out, and what he's then decided to do is to call function 1. Function 1 up here recreates the 3 variables, so these will be separate from these 3 because they're inside a different function, and then So he's had to redo this part again, then do the minus, and then print it out. And then from inside this one, he's called another function. So in effect, function 1 won't return until function 2 is finished returning. So we then go to function 2, and he's done something similar with that, and which then calls function 3, and so on. Now, when this is such a simplistic program, you can see that function 3 calls function 4 and so on. So it will actually work in this particular case. But the thing is that when it's a simplistic program like the one that we're after doing, it's not really necessary to break it down into functions, apart from to prove a point. But even in this case, the more appropriate way to do this, if you were going to do it, is that firstly, function 2 or function 1 or whatever should be given appropriate names. In other words, one should be subtraction, one should be addition, one should be multiply or whatever. And secondly, the idea of calling the divide one from inside the multiply one and so on, simply because that's the way they were done, that would mean that if you ever wanted to use that function again, it would always go and call the other ones. So the better way to do that would be to say, well, look, I'm going to cut that out of there, and I'm going to call function 2 from here, because it's this one that wants to do it. I'm going to cut function 3 out of there and put it here, and I'm going to cut function 4 out of here and put it down here. That would be the more appropriate way to do it, so that they don't all get spooled out in the way that they have been done. As you can see, it'll still do its job. That said, in this particular case, it's a little bit overkill, and it's unnecessary. But I can understand how, because I was showing functions, that you automatically went to jump to do that sort of thing. So it's not a problem as long as you realise that there's a much simpler solution to it. So that's the simpler integer operations. Now the next one I want to look at is this one, printing your name using single characters. Only a simple sentence written on this: write a program to print your name on the screen using character variables. Because I wasn't very specific in the way that I wrote that, and also because I think when I did the recording to do with characters, I emphasised a part that was perhaps not as important as I made it out to be. So we had some fairly unusual things happening. So firstly, I'm going to show you how I intended for it to be done, and we can then look at how people have done it. So there are two main ways that we could do it. We could use it with one character variable, which I'll just call letter, and I could write letter is assigned. And here's where a lot of people got confused. First letter of my name would be a capital S, and what I do is I put it in single quotes like that. Okay. Now, what people were doing were they were looking up the ASCII character set and looking for the S, which they found was decimal 83. So they were writing in 83 here. Okay, there's no need to do that. I emphasized that point in the recording, that everything is a number, simply so that you realize that was the case. But you make it easier on yourself in the long run. You just have to put it in single quotes when you're actually dealing with them as letters, and you let the compiler take care of the whole converting it into a number, because that's its job. So in most cases you don't need to worry about that. So the printf then single %C and letter. And then obviously that'll print out my S for me there. I'll just save this so. Okay, so we see the S has come out there on the screen, right? Now, to do the next one then, what you can do is, now obviously this is a very inefficient way of programming, but it's because we're starting, we have to start somewhere. So I can just put in the E. Now again here, what people were doing was to come up with some rather unusual things. I think in some cases people looked and said, well, the S is 83 and I want to get to a lowercase e, which is 101. So 83 from 101 is going to be 2728. And so what they did was they said letter is assigned letter plus 28. Okay, which which will work, right? But it's not really necessary to do that at all. So we'll just prove that works. Oh, I've gone one letter too. I've obviously gone one letter too far. Is it plus 28? I'll check that again. Uh, 101 and capital S is 83. I said 20. Oh, I said 27, and it should be 17 and 1 is 18. I should have said 18 instead of 28. Sorry about that. Okay, so we say SE is coming out, right? Now, again, that's not necessary. A simpler way, but still not the simplest way, it would be to just say 101, put in the number straight for an E, so that will also work. But again, unnecessary, because you don't need to go looking up that chart every time. Just put in an E like that and that'll do you fine. Okay? And there comes the SE. And so literally, you know, try and make life easier on yourself then, you know. Use copy and paste as much as you can. So I'm going to change that to an A, and that to an N. Then one thing that threw a few people was, how do we do a space? So that's handy enough. It's you literally just put a space character in there, and then we continue on. And Mullery has 7 letters in it, so I'll just put. Okay, so there I put in a M-U-L-L-E-R-Y and run that. So we see Sean Mullery comes out on the screen. Now, there is another mechanism to do it. What I'm just going to show you there. What I'm going to do is I'm going to cut everything from there on down. My mouse was long enough, right? And what we can do is we can literally make up what I'm going to do is I'm going to use a different name. I'm going to just call the first one C1, and then char C2, right? And I'm going to make Sean has 4, space is 5, and then Mullery is another 7, so that would be 5 and 7 is 12 altogether, right? Now, rather than putting them all on separate lines, if I was going to do it that way, what I can do is I can literally just put them one after the other. C2, comma, C3, comma, C4, comma. Now again, this is overkill for any normal program. It was really just what we were trying to do in this particular case, and that's 12 of them there. And what I literally do then is I can give a letter to each one. So C1 is assigned S, C2 assigned B. So there are them all written out. And if you wanted to be really efficient, you could say, well, there's C8 and C9 are both going to be L's, so therefore I don't need one of those. I could just use C8 twice or whatever, and that certainly would be the case. So what you then do is you put in %C several times. So we're going to need 12 of them all together, and then with the C1, actually what I'm going to do is I'm going to have that already done for me up here, and comes out like that. So let's give that a go, see if it works first time for me. And there comes out Sean Mullery. So that's another mechanism to do it, where you would use lots of different variables. You'd use 12 different variables. Again, you know, within a few weeks, all this sort of thing is going to be obsolete. It's certainly not the way you go about doing anything, but it's really just to prove the point. One last thing to mention here on this particular program is that because I've written such a long line here, I've gone across this line that's down the side of the screen there, which hopefully you can see that in the recording. You'll certainly see it if you ever open, if you open DevC, you'll see it put in there. That line is it's 80 characters from here to here, and that's effectively the amount of the text that will fit on a printed page if you print it out. So if you go beyond that line and you were to then print out the page, this part of the line here, or anything further that you wrote, would end up getting brought onto a new line in order to appear on the page. That will make things very, very messy when it gets printed. So a general rule of thumb is that that line is there as a kind of a border. Don't go across it if at all possible, and it's nearly always possible not to go across that. There's a neat way of writing it. So for instance, the printf here could actually be written like this. Okay, where we can clearly see the demarcation. These are the ones here, and then we have a comma, and then we've these ones here, and that's perfectly fine. That'll still work okay. So that would be an easy way to write it, and then it's very, very obvious. Whereas if we have a little bit of this brought onto a new line, it's a bit of a disaster. Okay. Now in some of the other programs here, characters as numbers, that's fairly similar to what you would have seen in the video. Special character constants, we looked at the /t, and what I'm going to do there is I'm going to just after, let me see, S-E-A-N, and that's the space, right? So that's the space, and then after the M, just for the sake of argument, I'm going to put in a /t here just to make the point. If we run that, we see that it creates a tab. Now remember, a tab is different from a space. It's not necessarily a certain number of spaces. It tabs over to a particular point on the screen, and that means that it's very easy to make tables and so on that all line up. So that's what the /t is useful for. The /a, hopefully you figured out what it's for. Okay. Now I don't know whether you hear that in the recording, but I could certainly hear it here. You'll notice nothing happens here, and I've seen a few people writing that down as an answer, that it gets rid of the tab or something, but of course there is no tab there. That A is an alert, so it makes the little beeper inside the computer go beep to alert you to something. So you can hear it there beeping, right? And I know that a lot of people, when they run that program and they put in the /a, they hear the beep, but they just assume that the computer is doing something of its own accord and that it's not them that's actually caused that beep. But that's in effect what it is. So it can be useful in certain situations where you just kind of want to almost draw somebody's attention to something, or that something has happened, that it goes beep. Particularly if, for example, you wanted to, you were asking the user to input something, that you might put a /a there to go beep, as if to alert them to the fact that they have to respond in some way. That said, it can be quite irritating if you've got a class full of students and 20 of them are all doing it at the one time. But in any case, that's what it's there for. Now the next one here is viewing numbers as hex. This is relatively simple, a simple program, but it takes a little bit of time to write it all out. Now, what I do in a later recording where I look at for loops and while loops, I show you the efficient way of doing this. So that'll be in a week or two's time. You'll be looking at that, or actually, when I say a week or two's time, it'll probably be this week coming that you'll look at it by the time you're watching this recording. So what I'm going to do is I'm going to quickly I'm going to pause here and write that program and just show you some of the things, and then I also want to look at Paul Brannigan's program that he uploaded. A very unusual thing has occurred in that in Paul Brannigan's program, so I just want to point it out to you. It's quite a complex problem that's in it, but I'll show you that when we get there. So I'll just pause here for a moment. Okay, so the beginning of the program has been written here. We've made an integer called num, and we've set num to 0. And then I'm printing it out as a %d first of all, and then as a %x. So I need to write that in twice, because even though it's num in both cases, this one goes into this %d and this one goes into this %x, so it gets interpreted as a hex number. Now, as it happens, 0 in decimal and 0 in hex are going to be the same thing in any case. So just to run that, see that 0 comes out in both cases, and you can see that they're tabbed apart there, and I've done that for a specific reason. Now, most of you will probably jump to the conclusion saying num is assigned 1 for the next case, and then doing it that way. Right, and that will indeed work. Okay, so we see 1 come out in both cases. Slightly simpler way than that though. You can either say num is assigned num plus 1, because it's going to go up in 1 each time, or you could say The simpler mechanism to do it is just say num plus plus, and that does the same thing. So it's going to go up by 1 each time, and that makes it very simple, because what I can then do is I can copy that, and I know that I can go 2, sorry, what I'm going to do is I'm going to copy all the way up to there, because it'll do it. Now I don't know how many I've done there, but I'll just run it and see the handiest way. Oh, and I've done it perfectly. We went exactly to F. So you can see how I speeded myself up there very, very quickly. Whereas if I had written each one of these individually, 1, 2, 3, 4, and 5, it would have taken me a good bit longer. Maybe only another minute or two, but minutes matter. You know, when you've things to be at. So we can see there we've got the decimal on one side and the hex on the other side, and they're tabbed apart quite nicely. What you can then do, and it's not a bad idea, is to put in a printf here with a heading that says C101 decimal, and I'm not sure how many of these tabs that I'll need, so I'm just going to have to see. It won't be as many as are there, because obviously the decimal takes up more space than that, and I'll put a hex here and /n. And I haven't done enough tabs, so I'll do another one. And there we have it. It's perfectly lined up over it, so decimal and hex, and we can see them nicely there. So that's the proper way to format that. Now that's the way to do it. As I said, I want to look at Paul Brannigan's one, so I'm just going to pause and open that. Now the way Paul has decided to do this is to create a function which adds 1 in each case. So that's similar to my plus plus in the previous case, and then print out the decimal and the hex together. He's called that number. Now what he does then is he sets number to 0 here, and he prints out the first one, and then he calls function 1, and he calls that function the next 15 times. Now this appears to work, which threw me, I can tell you, at first. So we can see that he's printed 0 twice, which is a bit of a nuisance, but other than that, it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 15 and F. He's created the character called number in 2 places, once up here and once up here. Now those will actually be completely separate from each other, so they don't actually meet each other. What should occur is that the number is created here and 0 is put into number, and then it's printed out, which indeed happens, and then we call function 1, and we go up here, we create a new character called number, but Paul hasn't actually given that any value. He hasn't assigned it a 0 here at all. And by pure luck, what occurs is that there's already a 0 in there, and in doing that, he then adds 1 to it, which becomes a 1, and it gets printed out on the screen. Now at that point, that character there, that character called number here, gets destroyed. It disappears. The memory is taken away. We come back from the function and we call function 1 again, and again he recreates the number. Now the thing is, it would be amazing that by pure luck the next time that it happened to be a value of 1, and then we'd add 1 to it and it would make a value of 2, and up we'd go in sequence. But in effect that's what's happened. What occurs is that when we recreate the number, the compiler just goes, oh well, that space that I used a minute ago was free, a little bit like a car parking space. That space a minute ago was free, so therefore I'll use it again. What happens to be sitting in there? Well, the last number that we used, which was the number 1, and because the number 1 is sitting in it, we add 1 to it, it becomes a 2, and now it prints a 2, and now all seems to be fine. We then destroy that, we get rid of that again, and we call the function again, and this time we recreate number a third time, and we recreate it in the exact same spot, and what happens to be sitting in there? Only the number 2. We add 1 to it, and it becomes a 3. and it prints out fine. So the program almost seems to be working perfectly. Okay. Now, the real problem that exists here is, firstly, what should have been done is that this would have been set to some number. But if I did that, it comes out much worse. We end up with a 1 in each case, because every time we recreate that, we just set it to 0 and then we add 1 to it. So clearly that wouldn't work. What should maybe be done is that you would write this as char number, and get rid of that, okay, and then pass in the number each time. So we could put in a 1 or a 2, okay, and in that case then we would also get rid of this, and that would work, right? Now, that's one way of doing it. Again, not necessarily what we want to do. What I'm going to do is I'm going to prove to you that this doesn't work, and I'm going to do it by making a second function. Void func2, and it's going to be a void as well. And I'm going to make a character called Sean here, and I'm going to set Sean to be a value of 54 for no particular reason. Okay. Now, function 2 has nothing to do with function 1. It creates a variable that's a completely different name. It sets that variable to 54, so it should have absolutely no effect. Now remember, as I run it at the moment, get rid of that because that's the way, back the way we had it. It seems to be working fine, apart from the fact that we have two zeros there at the beginning, but otherwise it seems to be going up in numbers fine. What happens is, somewhere in the middle of this, I decide to call function 2 for some reason. So in other words, I've added something to Paul's program here. Well, you notice here we go 1, 2, 3, 4, 5, 6, 7, 8, and all of a sudden we go to 55, 56, 57, 58, 59, okay? Despite the fact that that 54 has nothing to do with this thing, it's managed to jam itself in the middle. What has occurred is that every time function 1 is called, it recreates this variable here called number, and it recreates in the exact same spot, so it happens to be holding the last thing that was used. But if somewhere in the middle here I go and create another variable called Sean, that variable Sean goes and takes that space, and it puts in whatever number it wants, and then it goes and destroys it. It doesn't need it anymore, but that number is held in there, so that the next time function 1 is called and recreates number, it has the number that was given for Sean. So you can see here how if we don't actually pay attention to what we're doing, if we assume that the number will always be there, even though we've gone and destroyed it, we're going to end up with a bit of a disaster. Okay. Now there are ways of making sure that every time you call a function it retains the number that it had previously, but that's an advanced topic. In fact, most of what I'm showing you here is this somewhat advanced topic, so don't be surprised if you don't fully understand it. It's a little bit we're jumping a bit too far into the future, but I do just want to show that there is a problem with this program. It's quite an unusual one, and just to be wary of it in the future. Okay. Now going back to our assignments, the minimum field width one is simply just a formatting thing, so it's not a vitally important one, so I'm not going to take a look at that. I am going to take a look at the maximum size number. Now as it happens, I haven't looked through your programs, so I'm going to take a quick glance through your programs. I'm going to pause and take a quick glance through your programs, and then I'm going to show you what that was about. Now, by the looks of it, most people have got this correct, but there are a few that haven't. I noticed, I think Paul Culleton and Patrick Keedy, you had some numbers like 9999 and so on. I'm just going to have a look at them here. Paul Culleton here. Yeah, you see, so we've got 9999 and minus 9999. I'm just going to grab that number there and bring it into who's this? It's Donald Taylor's. I've used Donald Taylor's program rather than rewriting it myself. If I just put that under it here, you'll notice that that 99999 is actually a much smaller number than what Donald got away with using here. Okay, but what occurred was that when you added an extra 9 to it, all of a sudden it became a larger number than what we have here. The problem with using only nines and so on is that you're thinking in decimal, whereas you have to remember that in C programming on a computer you're dealing in binary, so everything is a power of 2. Now, as it happens, the number that we have here, 2147483647, that's one less than a certain power of 2, and I'm just going to see if I can figure that out. I'm going to assume it's 2 to the power 31, so on your calculator you could try 2xy 31 and then d correct with that. So just I'll open up the calculator here so that you can see it. And view scientific, and we'll say 2 to the power of 31. Now you notice integers in general are 4-byte numbers, which would be 32 bits. I'm only using 31 of them here. I'll explain to you why in a moment. But we get that number 2147483648. Okay, and that's what we've used up there on the minus number. Now what's happened is that in a 32-bit number, 31 of them are used for numbers, and 1 bit is used to tell us whether it's plus or minus. Okay, so if it's a 1, it's a minus. That may seem counterintuitive, but that's what it is. And if it's a 0, it's a plus. And what happens is we go from minus 2147483648 up to plus 2147483647, which is 1 less. Now you'll wonder, well, why is it 1 less on that side? Why isn't it an even number? You got to remember that there is a 0 in there in the middle, which is neither plus nor minus, and it has to be taken account of. It actually takes 1 off the plus side, so it's considered a positive number. Now, you may not have figured out that number, those of you that did it, you may not have figured it out from actually doing a power of 2, but that's where it comes from. What most of you probably did was you started off with a number like x equal to we'll say 5. Okay, and sorry, I'm not getting my microphone there. I hope that wasn't too loud. And if we run that, we can see that that clearly doesn't come out as the number it's supposed to be. So there's something there. There's something wrong there. So let's try a smaller number. Let's try 2. And we can see that that works. So does 3 work? No, it's clearly come out something a little bit barmy. So 2 is the best we have. We can now try middle number here, 5. Will that work? No, it's come out a bit crazy, so we'll drop that down to a 2. Drop it down to halfway, and again that's gone a bit barmy, so we'll drop it down halfway again, which is down to a 1, and that's come out fine. So you could then try the next number, put that midway at 5, so midway between 0 and 9, and again we've got a crazy number, so let's try halfway there. We'll try a 2, and that's come out fine. So try a 3. Again, that's come out fine. Let's try a 4. And that's come out fine. But we know that the 5 definitely didn't come out fine. So it must be a 4. That's that number. Okay. And again, the next one, then we change that to a 5 and we start running again. And we see that that's come out fine. So we go up the way this time. We midway between the two. We either try a 7 or an 8. We'll try an 8 here. Okay, and that hasn't worked, as we can see. So we'll try a 7. And that's worked fine. So you can work your way down and figure out the number by doing that mechanism. But as I say, it is actually a power of 2, so you'll be able to actually figure it out by any other means. Just to prove the point to you though, here's the number that we came up with. And we can see that that works. And yet if I add 1 to this, so if I make that an 8, it comes out as a minus number for that. Okay, and if I add a 9, it actually goes down 1 in value. It's the minus number down 1 in value, and that's actually the way that it kind of works. So that's as high as we can go. And then in the minus cases, what we've done is we have a function here that we're going to call that's going to do the minus 1 for us, and we can see that that's the largest minus number. Again, if I put 1 onto this, we can see this turns it into the positive number. So this is kind of circular in the way it works, but that's as big a number as we can handle. There are other ways of handling bigger numbers and so on, and we can also switch to floating point if we need to, which will be able to handle bigger numbers, but that's effectively where it comes from. Okay. Now the next program is Unsigned, which is to do with unsigned numbers. And what that means is, let's say for example in the case here, I'm not concerned about using minus numbers at all. I only want to use positive numbers, and I want to basically take that extra bit that decides whether it's a plus or a minus. I want to use that as a number. What I can do is I can set this unsigned int x. In this case, I'm not going to use this minus 1 at all. And what's the largest number I can do? Well, basically what I can do is I can take that this number and multiply it by 2. Well, the better way to do it is to do 2 to the power of 32. And so what I'll do is I'll grab my calculator once more. Calculator happened to be open there. So 2xy 32 equals 429,496,7296. Can I copy that out of there? No. Okay, so there I've put in that 2 to the power of 32 there, which is 429,496,7296. Now, that shouldn't work on its own because I haven't included 0 in that. That'd be if I was starting from 1, so I should take 1 away from that and make it 9,5, and I'll prove that to you. One of the things, and I don't remember anybody asking me this question, so I haven't actually taken a glance at your program, so I don't know how well people have done with this one. It may be one that you just jumped over in some way, or assumed that it was correct, so important that you take note here. The %d doesn't work in this case. %d is only useful where the number is a signed number. So what's happening is we're taking an unsigned number here called x, and we're interpreting it as a signed number. So you actually have to change that %d to %u in order for it to print out properly on the screen. And I don't recall anybody asking me about that, so I have a feeling that may have gone by unnoticed. So hopefully you'll pick that up now. So if I run that, we can see that it's actually fitted that number there. And yet if I go one number further up to that 6 there, we can see that it's gone back to 0. And that's because it's gone completely round the clock. It's a little bit like an odometer on a car, where it goes over the final value and it goes back to 0. Okay, so you need to use the %u in order to prove that point, and in doing that you can make a number twice as big. It can be useful in certain situations, particularly useful in embedded systems where you might be using a character rather than an integer, where you may only have and actually what I'll do is I'll just show you that, prove that point. So we'll make a char called x. The largest number you can fit in a character it's an 8-bit number, so it's 2 to the power of 8, which is 256. Take 1 away from that, that's 255. Okay. I think I can just use the %c with that, but let's see. Oh no, sorry, it's %d, sorry. Because it's obviously going to be smaller. Nope. I'll have to use the u. Okay, I have something odd going on here. Give me 1 second. Sorry, I don't know whether I have that paused or on pause now. Is that actually recording there for me? It is, yeah. So I'll just put in unsigned here. see the 255 come out there. Now I just want to check if that works with the ordinary percent D. I think it probably will because it's lower than the set of numbers that are required. It will indeed. Now, if I go to 256, what occurs? We can see that it's gone back to 0. Now, if I don't use unsigned for my character, if I just use the ordinary one there, we see some unusual things start to happen. Even the 255, we'll see what I get. I see I get a -1, and that's because it should only go from -128 up to +127. Now, they're very, very small numbers, but in embedded systems there may be reasoning whereby you will only be using quite small numbers. You want to use a character variable in order to use up less space, but you want to be able to give yourself the full extent that that the character can give you, and so therefore using an unsigned character may be quite useful in that case to double up the amount that you can get. Okay. Now the last program is the area and circumference of a circle, which I've given you the right program that computes the circumference and area of a circle to at least 4 decimal places. Now the reason I put that in, I said at least, so I don't mind it being more. I think some people got hung up on that and tried to get it to exactly 4 decimal places, which you can do. You can instead of %f, you can say %.4f, and that'll give you exactly 4 decimal places after it. Use the following formulas. The real thing I wanted you to do there, when I said at least 4 decimal places, was that when you defined pi, I didn't want you to just do it as 3.14. I wanted you to use more decimal places than that because you introduce quite a lot of round up and round down error. So there's a few people: Patrick Keady, Colin Lyons, Michael Riley, Donald Taylor. There may have been more. I just took a quick look there. It's not that your program is wrong. What you've done is fine, except for the fact that you should really put in more decimal places for your value of pi. So I don't know whose I've opened here. We can see a 3.14 there. Whereas if we look at some of the other ones here, I've picked a bad one there again. That would be better off to do something like that, 3.141592. So actually go and look up the number, right? As well as that, actually define the variable pi so that you can then use it later on. I noticed in that last one there, where you've just piled in the number 3.14 there. Now, this is what I'm going to end the recording on the first week's stuff, is a few little pieces of etiquette. Firstly, a number that just appears there like 3.14, apart from the fact that most of us would probably recognize that that's pi, that's what we would call a magic number, because it appears just in the middle of nowhere with no reference to it as to what exactly it is. So you should, if you're going to do it, say float pi 3.14159 or whatever it is the number is. I won't go looking for it there now. And then put the semicolon obviously there first, and then change that to pi. Okay, and you could do the same down here. Now, the other thing that I'm going to do here is I'm going to take this particular program an example, because this is one that I've actually taken down. I think I won't say who it is because I can't remember who it is. It doesn't really matter. What I'm going to do is I'm going to tidy this up in the way that I want to see your programs tidied from here on in. Okay. And you'll have noticed in the recordings that I tend to write my programs in this manner, so I want you to stick to it too. So first thing you should do is go and look at the tools and editor options. If auto indent is switched on, switch it off. If smart tabs is switched on, switch it off. Okay, it's not on mine because my computer saves my settings, and that'll probably be the same for you at home, but every time you log onto the machine here in the college it resets it, so that can be a bit irritating, but make sure you go and change it. So go to tools, editor options, get rid of auto indent and get rid of smart tabs. Now, so what I'm going to do is I'm going to just start tidying up this in the way that it should be. This is all a complete mess down here in the way that it's laid out. So what I'm going to do is I want everything tabbed in one space, which is that far there. Okay, and this then should be back here. So we can now clearly see that there's a function called func1. It starts here, okay, so that's the beginning of it, and it ends at this brace here. If that brace is somewhere out here, I can't spot it, and I'm going down, looking down here and looking for the next brace, and I think it's down here, and I've missed that main has actually started in the middle of it. So always stick to that criteria of having the brace straight down below where the function starts. Now some people work this mechanism here where they have the opening brace there and the closing brace here. That's fine. It's not generally the way I do it, but it's fine to use as long as you stick to that throughout. Okay. What you'll find when you go working in a company is that they will have their own particular style. There's no sense in us trying to prejudge what that style is going to be because we can't know in advance. But when you get in there, you will have to. They may insist on you sticking to that. So again, here I'm going to have my int main void starts here, and I start tabbing stuff in to this point. Okay. And again, that brace is down below main, so we can now see it's much neater than it was. The last thing is then you should probably split things up into, you've got your declarations up here, then you've got any values that you're giving things, you've got any calculations that you're doing, and then any printouts down below that. So you can kind of spread the thing out in that way. Maybe just leave a space between major sections of the thing. It's not vitally important whether those two there, same as up here, go together or whether they're separate. It's mainly just that you kind of split the program up into its functional parts so you can quite clearly see what's going on in each individual case. I'd maybe separate those out because one is a call to a function and the other is a printf. Okay. Again, try and include as much comments as you can in specific places where it's important that you try and remember something. Very easy when you're writing a program to assume that you'll remember how the thing worked, but you won't always. Another good idea, I said I wasn't entirely certain who wrote this program when I did it, so not a bad idea to make yourself a little comment header that you use every time. And you could have things in it like program name and its area .c, and you've got description, this and then programmer's name. I'll put in Sean Mullery on this one since I've gone and modified it. And no harm to put in a date. So today's date as I'm writing this one is 28th of October. So 28th of October 2010. And in some cases where you're writing big programs and you're making changes to them, it's no harm to have revision number. So it might be 1.0 in this case because it's your first run at it. And then obviously close off your comment. And then we have a nice neat little thing at the top, so when we open this we can see, okay, who's written the program, what's the name of it, when was it written, so that we can then go back and try and work our way back to finding the person involved and asking them a question if they've done something. You'll notice, by the way, I've written a little semicolon after Sean. I'm so used to writing C programs that I put semicolons after everything. So that's the neat way to write a program, and I'm going to, when it comes to an assessment, I'm going to start insisting on neatness and indentation and commenting. So commenting appropriate places. The other thing I'm going to insist on is proper names for variables. Okay, radius here is good, area is good, pi is good. Whereas if we decided to call that x and call that y and that z, there's no way I have of knowing that one is the radius and the other is the area, and so on. So steer clear of using inappropriate names. Steer clear of what I mentioned there earlier, putting 3.14 something in the middle of the program where it's no reference to what exactly it stands for. They're called magic numbers. Stay away from those. Indent your program properly, keep it neat and tidy, and make sure that you put in comment headers and put in comments at appropriate places. This is not just for the sake of it. It's vitally important when you're writing programs, particularly when they get much bigger, that other people can actually read them, because it can save them literally hours and hours of time in trying to track down a problem. If you have it written badly, it can be almost impossible to debug. So it's beholden on you to write your program neatly and properly and comment it properly when you do it. There's no sense in trying to send somebody in later to try and do that, because it takes up far too much time. So that's the end of the wrap-up lecture on the first week's programs. So hopefully you've tidied up any things that you didn't understand then in your first set of programs. So important that you keep all those in mind when it comes to setting the practical assessments that are going to come up. If you've spotted anything as I was going through these that you didn't understand, or particularly that you did wrong, it's no harm to actually go and change your program to the correct way, so that later on when you come back to look at it during an assessment or something like that, that you have the correct thing there rather than the incorrect thing. And always, of course, comment anything that you feel that you had trouble understanding in the first case, because the chances are when you go back and look at it again, it won't make any sense to you if you haven't commented it. Okay, that's it for this lecture.